Welcome to Operations and Supply Chain University. I'm Jerry Wright. This is Lesson 13, One Piece Flow. So in a traditional manufacturing organization, there's a lot of department specialization, or things are functionally aligned in silos. In this example, there's a mixing process, then there's kitting, and then there's assembly, and then there's inspection. Then they have a separate packaging process, then it goes to a labeling area, and then there's material handling, and it finally gets to finished goods. In a lean manufacturing organization, we have a cell team or a module. Some people like the term module. I say cells. So in the cell team, we mix and assemble, we inspect and package, we label, and then we prepare for shipment, all in the cell team. So material handling is essentially handled by the cell team. We don't do a big batch. We do one piece at a time, one piece flow. Quality is built in. We inspect as we go. We don't have a separate department. Now you can have an auditing, an AQL, or some other random inspection, but in general, we build the quality in. That's the only way you can do it. You cannot inspect quality into the product. And then kitting is essentially eliminated. All these extra steps are gone. We have a much more efficient process. So one piece flow cellular concept is like this. We have multi-skilled employees and managers. The cell is responsible to build quality into the services or the product. Cross-functional teams are located together. Standard process operations. The customer is linked to the process, meaning we can see what the customer wants or what has shipped and replenish it. It's also linked to suppliers. We have a pull system or one-item transactional flow. That's the ideal cellular concept. So what does a cell look like when we think of cells? Typically, they're U-shaped or they could be a straight line. In my experience, a straight line's good for up to about 3 people. And then after that, it needs to become an L or a U. And that's largely to keep people close together for communication. That's the main reason to do it, is communication. We want to have a layout of sequential operations. You can see 1, 2, 3, 4, 5, 6. We want to go counterclockwise whenever possible. That's because most people are right-handed. We pick up with our right hand, we discard with our left. 85 to 90% of the world is right-handed, so we want to do right-hand pull. Equipment and workstations are close together to minimize walking and improve communication. And then the last station is close to the first, again for communication, line clearance, whatever's necessary. From start to finish in production, all the operations are completed by the cell team as much as possible. And the cell is based on the pace to meet demand, or what's known as takt time, T-A-K-T, takt time. So here's a couple example manufacturing cells. The one on the left is the Iceman production cell at DJO Global. And I don't know if you can see on this particular thing, but on the little score counter there, it says they should be at 71 and they're actually at 73. They're slightly ahead of pace. I don't know if you notice in this particular, this is a counterclockwise cell, all the operators are standing and they just build or work on one piece at a time. There's no batching. It's all one piece flow. And this other one, which is a stand-up cell making, it looks like a DonJoy ankle brace, again, courtesy of DJO Global. They have a stand-up cell and everybody's close together doing stand-up assembly and sewing. Now, it's not just manufacturing cells. There can be office cells. This is an example of a work cell at Menlo Innovations where they do software coding and programming for customers. So again, it doesn't always have to be manufacturing distribution. It can be all kinds of cellular teams. So what's wrong with this picture? This is one of my favorite pictures. This is from the days at the company I worked for. Many years they were making those walking boots you'd get if you had an ankle problem. And if you notice, you can see the arm of one lady on the far left side who's doing the assembly, and the one in the foreground on the lower right, she's actually doing packaging and inspection. So she takes the boots, she inspects them, and then she puts them in a plastic bag and then puts those in a box. Now, I came upon this and said, why do we have all these boots stacked everywhere and they're not working together? So, oh, well, you know, it's much more efficient to batch everything. I'm like, oh, no, this is not lean. We don't want to go in this direction. Imagine in this situation that one of the flaps is wrong or they put the wrong buckle on or something's incorrect. they have to then rework every single one of those. They have to pick it up, fix it, and then put it back. And it's taking a ton of space. I think if you count it up, there's well over 50 of these things that have been built, but not yet packaged or inspected. What we did over time is we made the table smaller, we put people together, and we moved into one piece flow because the quality is much better, the efficiency is much better, and think of all the time it took to stack and unstack all those boots. It's completely wasted time. Now, sometimes we're not dealing in manufacturing, we're dealing with complaint forms, or we're dealing with things that are in our computers and they're not on our desk like the papers you can see in this example. The thing I want to point out is batching is a problem. We really want to get to small batch or one piece flow if possible. Every time that we batch, we lose time switching applications or picking up and setting down items between processes. How much time is lost each day for an 8-person production line team if they only lose 2 seconds each time they stack the boot and then unstack the boot in that example of components while doing 300 units in a 6-step assembly process? Just think of it as one shift, and each person has to handle all these different things. Now, I know this seems crazy, but it's actually 8 hours a day. That's one full person. So I'm going to show you a video. It's a popular one you can find on YouTube. And it basically shows on the bottom an example of one piece flow, in the middle 5-piece or a batch of 5, and in the top 10-piece flow. The video only takes 1 minute, but you'll see how quickly things move through the one-piece flow and how soon the entire lot is finished, where when we do the batches, there's so much waiting. Each process, there's 3 processes, each one only takes basically 1 second in all 3 scenarios. So the processing time or the cycle time is exactly the same, but because of batching, we're waiting before we move things and it's much slower. Let's watch. So on the one-piece flow, we're done in 29 seconds. We don't even have a single item finished yet in the 10-piece flow. Finally, one's finished. The batch of 5, 41 seconds. And the batch of 10, a minute. So thanks to BMGI for this video. I think it's very illustrative. The other thing to think about is think of how much work is in process in that video. It's just pretty crazy. So we need to think differently, and this is what I challenge you to think about related to one-piece flow. If I only have to touch it once or not at all, that is ideal. Whatever it is, whether it's a form, a paper, a component, an item, whatever it is, if I only have to touch it once, that's ideal. If I don't have to touch it all, even better. But we're assuming it's required. If I can touch it 2 times, that's okay. If I have to touch the same item, the same form, the same order 3 or more times, it's not good, or it's an opportunity to improve flow. So that's the concept I want you to take with yourself as you think about one-piece flow going forward in whatever you do. Now, one-piece flow, in terms of cellular design, this is a good book to refer to. It's Kenichi Sakai. You can read more about one-piece flow there. All right, that's it for this lesson. Thank you.